All right, let's look at another example about how we can find solutions to linear equations. Okay, so that's what we're expecting. I probably won't make it through all 10 this time. Maybe I'll do 8. I don't know. We'll see. But I want to show you something. Again, my comfort level is always inputting numbers for x. Okay, so if I do that, let's say I put a 0 in for x, I would get 0, and maybe I'm going to go keep change, and make that plus a negative 5 times y equals 11. Well, that 0 cancels out, and I'm going to divide both sides by negative 5, and that's not that pretty. That's like negative 2 1/5, negative 11/5. Something we can do. Well, let's try one more. Okay, it's not bad. I'll put 1 in. I keep with purple. So if I put a 1 in for x, I'm going to go 1 plus, again, negative 5 times y equals 11. What's happening here is I'm getting two-step equations. So I'm going to subtract 1 from each side. All right. And then I'm getting what's left here is negative 5y equals 10. And then I'm dividing both sides by negative 5. 10 divided by negative 5 is a negative 2. This is totally legit, but it's a two-step equation. What if, instead of inputting numbers for x, we inputted them for y? So let's say I put 0 in for y. Okay, so I'm going to say x plus, because I made it into addition problem, don't have to, but it's helpful, a negative 5 times 0 equals 11. All right, in this case, x equals 11. What if I said I wanted to put a 1 in for y? I would get x plus negative 5 times 1 equals 11. Well, x plus negative 5 equals 11. I would just have to add 5 to both sides. And I get x equals 16. One-step equation. So you can go either way, and it doesn't matter. As long as you do the math right, you're going to get the right answer. But I like the one-step equation part, even though it goes against my comfort level. We're going to push outside our comfort level. Okay, let's say I put a 2 in here. I know there's not a lot of room, guys. I'm sorry. X plus negative 5 times 2 equals 11. Well, that ends up being x plus negative 10 equals 11. And if I add 10 to both sides, and I'm squeezing it in, I'm sorry, that's 11 plus 10 there. That ends up being 21. Oh, I had some different colors here. Negatives? Let's try some negatives. Let's put a negative 1 in. So let's say I go x plus negative 5 times negative 1 equals 11. X plus negative 5 times negative 1 is going to be a positive 5 equals 11. And I'm going to say here, what number plus 5 equals 11? And hopefully you'll tell me 6. I did negative 2. How about negative 3? Let's go x plus negative 5. I know I keep adding parentheses and not adding parentheses. It's just what I end up writing. I don't know. Equals 11. Negative 5 times negative 3 is a positive 15. So x plus 15 equals 11. What number plus 15 equals 11? It's a negative 4. Or you can subtract 15 from each side. And you get a negative 4. All right, and then let's just one more and I'm done. Let's go negative 5. So I'm going to plug in negative 5 in. I'm going to go x plus negative 5 times negative 5 equals 11. That's x plus 25 equals 11. And then I subtract 25 from each side, and I get my x value of negative 14. All right, you guys get the idea. But all of these here are ordered pairs. This one's a little tricky to graph. We can do it. But that's why when you have a variable by itself, it's nice to plug things in the other variable. But let's go 1 and negative 2. We should have enough here to get a good idea of our graph and what our graph looks like. Hopefully we're all anticipating that it's a line, right? Linear means line. Okay, so let's go start plotting these. 1, negative 2. So I'm going to go 1 to the right, negative 2 down. Guys, this is why it's so important that we understand graphing coordinate planes. I'm not going to worry about that 0 and negative 11/5. Let's go 11, 0. 11 to the right, 0 up and down. 16, 1. So I'm going to go 16 to the right, 1 up. 21, 2. Go 21 to the right and 2 up. Does it look like we're getting a line here? Hopefully it does. 6, negative 1. I have negative 4, negative 3. Okay, negative 14 I can't do, but it would look like it'd be on the line. So again, guys, we can plug things in for x or for y, and sometimes it's easier to do one or the other. Kind of like with fractions, it's easier to do multiples of the denominator. But when we graph this, what shape of the graph is the linear equation taking? It's a straight line. And honestly, I usually just write line because all lines are straight, but sometimes we say curved line or something like that. Okay, so we get that when we graph these linear equations. Now I'm going to go back. I want to look here at both of these. Notice here that our linear equation, x is to the first power and y is to the first power. Up here in the first one we did, x is to the first power and y is to the first power. Remember, when our variable terms are to the first power, the graph is going to be a straight line. So if we look at this next example here, it says Joey predicts the graph of negative x plus 2y equals 3 will look like the graph shown below. Do you agree? No, you don't agree. And here's the reason why. If we look at this graph, okay, I can see that my x term and my y term are to the first power. Remember, that means linear. Okay, way back in the beginning of Module 4, we were translating from words to math symbols, and then it would say, tell if it's linear or nonlinear. And you would say, it's linear because the variable terms are to the first power. Nonlinear because they're raised to anything else. So we're going to say linear, and we're going to say the variable terms. Now, if this was 3 to the second power, I wouldn't care what that is. I'm only concerned with the variable terms. Variable terms. Sorry, I'm hitting buttons on my stylus. Variable terms are to the first power. Okay, so if it's not a straight line, okay, if the points don't all lie in a line, there's nothing wrong with it. It just means it's not linear. All right. We've looked at some equations that appear to be lines. Can you write an equation that has solutions do not form a line? Sure. Anything that has variables that aren't to the first power. Now this one's to the first power, but that one isn't. Y to the third plus x to the second equals 1. Anything that if you have at least one variable term that's not to the first power, it's not linear. Let me show you a quick example of why that is. Okay, let's say I had this equation, y equals simply x to the second power. Okay, oh my goodness. Move your hand, messing. Okay. If I put 0 in, I would get 0 to the second power, which is 0. Great. If I put a 1 in, I would get 1 to the second power, which is 1. 2, I'd get 2 to the second power, which is 4. Now, what if, though, I get some negatives in here? What if I said negative 1? Well, a negative 1 to the second power, remember, means negative 1 times negative 1, so that'd be a positive 1. If I did negative 2, I'd go negative 2 to the second power, negative 2 times negative 2, which is a positive 4. So these points are 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. So if I were to sketch a graph, and you know me, this is going to be rough, and plot these points, zero, 0 is going to be right here. 1, 1, 1, 1 on my very rough graph. 2, 4, 2, 4. Negative 1, 1. Negative 2, 4. You can see how we kind of get this U shape right here, right? We're going to get more into that later. Nothing wrong with that, but that's why it's not a linear equation. It doesn't form a straight line. And so that's why we're always going to say the variable terms are to the first power. If it's linear, it's a straight line.